People who use buffers understand that they limit pH change, but most of them don't really understand how that works. The purpose of this lecture is to explain just how buffers limit pH change. I'm going to be doing some calculations quickly in this lecture. Please pause it at any time to convince yourself you understand the calculations. So first we'll look at the pH change when you add acid and in a minute to base to pure water. So let's start with 1 liter of water, so that the volume is 1 liter and the pH of pure water is 7. What happens to the pH when you add 1 milliliter of 1 molar HCl to the water? We're going to use the dilution formula to see how the HCl concentration changes and to calculate the new pH. Okay, so we're diluting 1 milliliter, so the initial volume of the acid is 0.001 liter. The molarity is 1 molar. We're diluting it to a new volume of 1 liter. And so how does the concentration of HCl change? What's M2? So you're using the equation and the substitutions, you find that the new concentration of HCl is 10 to the minus 3 molar. That is, we're diluting the HCl from a milliliter to a liter by a factor of 1,000. So sure enough, the concentration goes down by a factor of 1,000. So the new concentration of HCl is 10 to the minus 3 molar. Since HCl is a strong acid, it dissociates completely, so that means the H plus concentration is 10 to the minus 3 molar, and the pH has gone from 7 in pure water to 3 after we've added a milliliter of 1 molar acid. We can do a similar calculation to see how the pH changes when you add strong base to water. Again, we'll start out with 1 liter of water, so V1 is 1, and the pH is 7. We're going to add this time 1 milliliter of 1 molar NaOH, and we'll use the dilution formula. So our initial volume of NaOH is 0.01 liter, that's 1 milliliter. The molarity is 1 molar. We're diluting it to a volume of 1 liter. So how's the concentration of NaOH change? Calculate M2. And using substitutions, M2 is 0.01 molar. So again, we're diluting the NaOH by a factor of 1,000, so the concentration goes down by 1,000. In this case, the 10 to the minus 3 molar is the concentration of hydroxide, so the H plus concentration is 10 to the minus 11. The exponents add up to minus 14 in pure water. So that means if the H plus concentration is 10 to the minus 11, the pH is 11, and the pH, when you add this 1 milliliter of NaOH to water, the pH goes from 7 to 11. So now we'll think about how buffers work. Buffers are solutions that contain a mixture of a weak acid and its conjugate base. Some examples might be acetic acid and sodium acetate, or carbonic acid and sodium hydrogen carbonate. So what happens when you add acid or base to a solution of buffer? Well, the added acid, the H+, reacts with some of the conjugate base that's in solution to convert it to HA. And similarly, when you add strong base to a buffer, it reacts with some of the HA in the buffer to form water Na-. So notice, adding strong acid and strong base don't affect the water directly. They're actually just changing the HA-A- ratio. Acid converting some of the A- to HA, and H- converting some of the weak acid to weak base. So now, how are we going to do buffer calculations? Let's derive the equations used for buffer calculations. We'll start out with the dissociation equation for a weak acid. And notice then the Ka, the equilibrium constant for that, is H plus times A minus over HA. And then I'm going to form an equation I call the handy equation, just to give it a name, where I divided both sides by H plus. So notice that now we're looking at the A minus HA ratio, which is the same as the Ka H plus ratio. Now if you take that equation, take the log of both sides, do a little subtraction, you end up with the Henderson-Hasselbalch equation. And don't take my word for it, do the algebra and derive the Henderson-Hasselbalch equation yourself. So we're going to use the Henderson-Hasselbalch equation and the handy equation. Now, applying the equations, when we're going to apply those equations when the A minus and the HA concentration are the same. So we're going to, so for example, the Henderson-Hasselbalch equation says the pH is equal to the pKa plus the log of the ratio. Now, so in our buffer, if the A minus and the HA concentrations are equal to each other, that means that ratio is 1, the log of 1 is 0, so we formed a buffer where the pH is equal to the pKa of the weak acid. Similarly, using our handy equation, when the A minus and HA concentrations are the same, and the ratio of them is equal to 1, notice this time you don't even have to do logs. You can just see that when the A minus HA ratio is 1, the Ka H plus ratio is also 1, so the H plus concentrations is equal to the Ka, which is really the same result. The pH is equal to the pKa. Now, before we start doing calculations for buffer, I want to just mention a little shortcut, a calculation shortcut that makes life a little easier. Now, we've been using brackets, which is concentration in units of moles per liter. Now, so when you take the A minus HA ratio of a buffer, the A minus is in moles per liter and the HA is in moles per liter. Well, those liters are both the same because the H plus and the A minus are in the same solution. So since the denominators are the same in both cases, you can, for the A minus HA ratio, you can just use the ratio of the moles. And that makes life easier because if the volume happens to change during your calculation, you don't have to worry about what the volume is because it's going to be the same for both A minus and HA. So the ratio is just going to be the ratio of the moles. And now we're ready to calculate how the pH changes when you add strong acid to a buffer. As a buffer, we'll start out with, we'll use a mixture that has 0.1 molar acetic acid and 0.1 molar sodium acetate. The pH of acetic acid is 4.75. So as we've shown before, since the concentration of weak acid and weak base are the same, the buffer is going to be the pKa. So the pH of this buffer is 4.75. Okay, so and so if you have 1 liter of this buffer, we'll start out with 1 liter like we did before, and it's at pH 4.75. It's going to contain 0.1 mole of acetic acid and 0.1 mole of sodium acetate. When we add our 1 milliliter of 0.1 molar HCl to our buffer, 1 liter of buffer, starting at pH 4.75, we're going to be adding 0.01 mole of H+. So the added HCl that you're adding to this, the HCl you're adding to the buffer is reacting with some of the A minus present to form more HA. So a little bit of the A minus that's in solution is going to be converted to HA by the acid. So your moles of HA are going to go up a little. We started out with 0.100 moles of HA in our buffer, and we're adding 0.001 moles from the HCl. So now we have 0.101 moles of HA. Similarly, we've used up a little bit of our A minus. The moles of A minus are going from our original 0.10 moles down by 0.001. Now we only have 0.099 moles of A minus left. So we'll use the Henderson-Hasselbalch equation to see how the pH has changed. And not surprisingly, you can see that the A minus HA ratio has not changed very much, so that our pH has not changed very much. And so adding that 1 milliliter of acid, which made the water go, remember, from pH 7 to pH 3, when you add that same 1 milliliter of acid to our buffer, the pH goes from 4.75 to 4.74. So what you can see from the Henderson-Hasselbalch equation is that unless the A minus HA ratio changes by an order of magnitude, that is a factor of 10, the pH is not going to change by, you need a change of a factor of 10 to change the pH by 1 unit. So if it changes by less than 10, the pH is going to change by less than 1 unit. So, in conclusion, buffers resist pH change because added acid or base don't affect the pH directly. Added acid or base just change the ratio of the weak acid to its conjugate base that's in the buffer, and until that ratio is changed by an order of magnitude, the pH doesn't change that much. In a separate lecture, I'll try to simplify solving buffer problems. Thanks for listening.